Hey guys, this is Saptarshi here and welcome to our YouTube channel. So last few video tutorials we have looked at convolution neural network and we are today going to focus on pooling, which is one of the very important operations of CNN. We'll very briefly touch upon a simple operation called as flattening. So here is a recap of your CNN architecture. So you have an image as an input. So here you see image of a cat and you need to classify whether the image is of a cat or not. Okay. So you have your feature extraction layer and you have a classification layer. The feature extraction layer actually have convolution modules and each convolution module has a convolution operation and a pooling operation. Okay. So basically this first convolution module will find lower grain features, and as you move through the CNN layer you will go for more higher order features. So you may be starting with edges and then you will go to nose, mouth and all these higher order features. Okay, and today we are going to focus on this pooling operation. Okay, so let's look at this very closely now. So like in case of your filter operation, your image or your input is a 2D metric, output is also a 2D metric, and this also works on a sub part of the image or a region of the image. Okay, and that is defined by the size of the kernel. So in this case the size of the kernel is 2 by 2. So I will go to top left and I will select this 2 by 2 portion and I will look at which is the maximum value. The maximum value is 8. So this 8 I will take and I will put in the top left square or top left cell of the output. Okay. So next I am going to consider another adjacent 2 by 2 metric, right? And here I can take a stride of 1, start from this 3, or I can take a stride of 2 and start from here. Okay. So what is the maximum value over here? The maximum value is 6. So I will put 6 over here. And similarly, I can get 9 out of here and 9 out of here, right? So that's how you are forming the output. So how do you describe this pooling operation? So the first is you are taking the maximum value. So you call it as max pooling. What is the kernel size? It is 2 by 2. What is the stride length? It is 2. And are you applying any padding? No. Okay. So this describes the entire pooling operation. All right. Now what is the effect of pooling? So the first effect is that it has drastically reduced the size. And so there is a 75% reduction from the original image if you see. And however, if you see this particular image and a pooling has been applied, do you see a lot of loss in information content? No. So that is what actually your pooling layer strives to do. It takes lesser memory because of this subsampling. The computational load goes down and subsequent layers will also need less number of parameters. So less number of parameter means less tendency to overfitting. Okay, we will evaluate the striding strategy in more details now. All right, so here is a input image, okay, which is a 7 by 7 metric, and your kernel size is 3 by 3. So again I will go to the top left and let's apply max pooling. So what is the maximum value? The maximum value is 7 and I put 7 over here. And similarly I go ahead and I get this output metric. Okay, so this is when I apply a stride equal to 1. And when I apply a stride equal to 2, this is my output result. So what is my conclusion? The first conclusion is that actually if I increase my stride size, that directly has an effect on the reduction of the image. Not only that, if you look at this image, then there is a lot of redundant information. You see that there are adjacent 7s over here, then you have adjacent 5s, and then you have adjacent 8s, and so on and so forth. Whereas there is very less amount of repetition in this particular output. So naturally you can conclude that having a higher stride size is probably better. Okay. So the guidelines are like this, that convolution operation, the stride size is typically 1. So here it is recommended that stride size should be greater than 1. Okay, 2 is a good size, 2 is a good stride size. And if you are going for a very high size kernel, right, partial overlap is good. Okay, less non-overlapping is better, but little overlapping actually turns better when you try to handle problems like overfitting. Now we have looked at max pooling, which is of course the most popular pooling operation, but there are couple of more operations, which is mean pooling and average pooling. And as the name suggested, in mean pooling, you are taking the minimum pixel value of the patch. In the average pooling, you actually sum over the intensity values and take the average, right? So let's see what is the effect of that. So here is an original image over here. And when we apply max pooling, do you see what is happening? The image is, somewhat kind of brightened because you are taking the maximum pixel value. Average pooling, it is almost similar like the original image. Probably it has become more clear. And minimum pooling, you have got a kind of little bit of patchy image. Okay, so there are some kind of noise or some kind of disturbance in the image, right? So you might think that whether all other poolings are required or not. Okay, so average pooling actually smooths out the image and hence the sharp features may not be identified. Okay, so max pooling actually has this advantage. So as it selects the brighter pixels, it identifies the more strong or more sharper features. Okay, and when you can apply max pooling, so when the background of the image is dark and we are interested in the lighter pixel, then max pooling is best fit. Okay, and example is your MNIST. Similarly, mean pooling can be used on the other way around. So the background of the image is light and the image is darker. So there you can use mean pooling. Okay, so for a lot of time actually average pooling was the one that was being used, and later on people shifted to max pooling because max keeps the strongest feature. It is slightly less expensive to compute and offers strong translation invariance. So this is what we are going to take a more deeper look. What is this invariance all about? Okay, now let's look at this particular image. Okay, so you see here the image or the pattern that is there is the darker image, and if you apply a max pooling, actually you lose the image. Okay, so this is something very important to notice. Whereas if you do an average pooling or a mean pooling, you can at least get the shape of the image, or you can understand there is something there. Similarly, the converse picture, if you have something like this, okay, max pooling can identify something. However, mean pooling cannot identify anything, and average pooling can do a decent job, right? So you really need to look at your image and decide what kind of pooling you should go for. Now, what do we mean by translation invariance? Okay, so look at this very carefully. So let's say that this is your input to the pooling layer. Okay, and this is one input, this is another input, right? And if you apply pooling, you actually get the same output. So what is the significance? The significance is that in an image, if there is a cat, even if it is shifted little bit by 1 or 2 pixels, it still remains a cat. Okay, so convolution actually helps you in that, because both the cat's picture, even if it is shifted by little bit, is converted to the same image, right? So that makes it invariant to translation. Okay, and it also offers little bit of rotational invariance and slide scale invariance. Okay, and here is a quick comparison of pooling versus convolution. Okay, so you might say that I can increase the spatial footprint by both convolution and pooling, right? Because I am looking at a patch of the image, I am taking one of them. Again, in the next layer, I am looking at a higher order image, right? So we are increasing the spatial footprint. And strided convolution, right? So you put a lot of stride in the convolution. That may be an alternative of pooling. So people have done experiments on that, and they have seen that in some cases it works, but pooling actually gives you more generalized results. Okay. So here is a quick note on rotation variance, and we also wanted to highlight about certain other things. Okay. So it depends on what kind of task you are looking at. So if you are looking at an image classification task, so this particular thing, right? So this is an input image 3, but it is rotated, and you can, if from the rotated image also you can identify these as 3, then your operation is actually invariant to rotation. Okay, but this is typically when you are doing a task like image classification. Okay, but sometimes your orientation may be important, right? So when orientation is important, so let's say you are looking at a car's position, and maybe you want to do some kind of automated traffic signaling or automated parking, where you actually want to know the orientation of the car. So there, you want to find out that this car is actually at 45 degree and this car is actually at 90 degree. So the orientation is important. So this you want to detect. This is called as covariant. And then there is another thing which is called as equivariant. Okay. So equivariant means that if you change a little bit in the input, there should be a corresponding little bit change in the output as well, right? So when you are interested, you are looking at different objects and their relative positions, right? So your objective will be equivariant. So what we want to tell is that yes, invariance that is introduced by pooling is good, but you will also have to look at what kind of image task that you are doing. Now we will come to something called as global average pooling. So this is a very interesting concept. So far what we were seeing was that you have a kernel size, and based on the kernel size you are using your pooling layer, right? So that's what actually you are doing, right? You are maybe selecting this part and selecting one of them. In global average pooling, actually you are pooling on the entire feature map. So you assume that your kernel size is same as the feature map size, and if there were 3 feature maps over here, for each one of them you just get one value. So you might be saying that this is actually very distracting. You are right, but it turned out that there are some applications of global average pooling as well. Okay, so some cases it has been seen that the global average pooling layer actually can substitute the classification layer. So you have convolution layers, okay, and you have not kept the pooling layer, which you can keep. And finally, you have a global average pooling layer. And if you look carefully, as this is a image classification problem, there are 10 classes. So in the last convolution layer, you have a 10 feature map, and for that 10 feature map, you have a global average pooling done. So you are getting kind of a vector which has as many elements as the number of classes in the problem. Okay, how this is used by the softmax layer? Simple. So you have this outputs coming from your activation layer. So this is what you have in your gap layer. Okay, and then you are applying softmax function, and you can see that the highest value that you get is 4.1. So the corresponding probability is highest over here. So you don't need a traditional classifier. Directly you are using this global average pooling with a softmax function, and you can understand that this is computationally much more better, right? Much more better, and often it gives good result also. If you want to look in more details, you can refer to this paper, Network in Network by Lin, Chen and Yan. Okay. And now the flattening part. So as you know that the pooling layer will give you a 2D metric, and flattening simply means that you go like the rows. Okay, so you will take 1 1 0 over here, then you will go to the next row, you will put 4 to 1 and then 0 to 1. So this is simply a mechanism to convert a 2D matrix in a 1D matrix. Okay, so this is what we have to cover on convolution. I hope you have got some good understanding, and if you have any questions, please give that in comment section. We will very much like to answer them. Thanks once again guys for watching this video.